In this computer lab, we are going to look at the problem of a 3-point and 4-point bending test for aluminium and also aluminium with oxide coatings. And the size of specimens is in this paper showing here 123 millimeters. And here are the settings of the 3-point or like a 4-point test. And so first step is to in ANSYS Workbench, we need to set up the materials. In this case, we have basically two types of materials. One is aluminium, so this like AA 1050, and basically we need to know isotropic elasticity. And so here is the Young's modulus and then Poisson's ratio. And there is also like a density given here. So note the unit is ton per cubic millimeters. And for alumina, that is aluminium oxide. So this is obtained from Granta. So from Granta design typical material. So we are just going to use that one. And the next step is to set up the geometry. So in geometry, the aluminum plate is actually being modeled as like a 2D like shell structure. So like for sketch 1, so that is actually the sketch. And basically from the sketch, a rectangle, we can create a surface body. And secondly, we so model like two supports and one loading node. So using solid like geometries, so cylinders. So this like distance between the bottom two rollers, that would be H3, 60 millimeters, and the diameter of the cylinder is 10 millimeters. So this is a combined shell and solid like geometry. So in total we have 4 parts. One part surface body for aluminium, and 3 solids for 2 supports and 1 loading node. So in ANSYS Mechanical, there are a few things that need to be set up. First, in geometry, we need to specify the thickness here, so that 3 millimeters. So for the surface body, and here we also need to select the correct material. So that is AA 1050, that aluminium. And also here we have like offset type. And if you wish, you can also adjust the offset type. So because we model this as a shell, like a 2D, like a surface, so this is actually the mid plane. And if we go to the mesh, we can see that it actually here is the mid plane. And if we look at the like mesh, we can see there is some overlap here, overlap there, and because that is the thickness. So this actually doesn't matter, and so won't affect the analysis. So after that, like an important step is about the contact. So we have a few contact areas. So first, we can see that like this is between the bottom, like surface, and the support on the left. And the second one is on the right, and the third one is the top surface and the top roller. So for all of these contacts, and I I used frictional contact with a friction coefficient 0.2. And in addition, for the interface treatment, change to adjust to touch. And I think by default should be at offset, no ramping. So a better setting should be adjusted to touch. And for all of the three like contacts. So changing to a frictional will enable like when the plate is being bent and there will be sliding occurs like between in here and there. So here is the mesh. So just use the default one. And for the boundary conditions, first fix the bottom two rollers. And for the top roller, define the displacement only allow the vertical, which is in negative y direction, so 10 millimeters. X and Z displacements are constrained to zeros. And so far, we only applied uh, boundary conditions to the rollers solids. So in order to like ensure that the this aluminum plate is in its place, so I used the remote displacement and constrain uh, like all these like degrees of freedom, and the only remaining one is like a y component. So y can actually move downwards, and also the pinball region. So instead of like the whole like plate, apply to like a radius of 5 millimeters area. And so for analysis, you could let the computer program to decide like how fast you apply this load. So this is called program controlled. And you can also do like the manually define the time stepping by defined by sub steps. So in this case, initially we set up 10 sub steps and with minimum number of 10 and maximum 1000. So when there is like some convergence issues, and the program can increase the number of sub-steps for better like convergence. And solver type, weak springs, and pivot checking, leave this to program controlled. And large deflection needs to switch to on from off to on, so that will be nonlinear analysis. So all the others leave as default. So after this, we can solve the problem. So now we can look at the like results. First, we have the normal stress, and then we have directional deformation and reaction force. So if you take the data here and look at the time and in this case minimum displacement, this data can be copied to Excel spreadsheet. And reaction force is using the same like time reference. So it can also be copied to Excel spreadsheet. So we can get like force displacement curve based on the from the simulation. So here I like to show you. So far we did like only pure aluminium. So if we have like coating either on bottom or like on the top, and we can actually modify the geometry here. So in geometry, and we actually don't need to change the thickness here, because here we can actually right click to I think it's right click here, insert, and the layered section. So in the layered section is defined by a worksheet. So the worksheet you can see at the bottom is alumina. So it's 0.04 millimeters. And then on top of alumina, we have aluminium, like 3 millimeters. So this is like there is a coating on the bottom. So after that, the remaining steps are exactly the same, and we can look at the stress. So you can see because of the high stiffness, we see the very large stress, like in the coatings, and also the displacement and the reaction force. So the other like modules are quite similar. This one is a coating on the top and the coatings on both bottom and top, like a sandwich. So all these like different modules and have the same engineering data and the same geometry. So all being shared. Like you can see all these lines means and that they are being shared.